Combinatorics is the mathematics of counting, but not counting one at a time. It's counting cleverly, using structure instead of brute force. There are two core objects here. A permutation, written P of nr, counts ordered arrangements, how many ways you can arrange R objects chosen from a pool of n, where the order matters. A combination, written C of nr, counts unordered selections, how many ways you can choose R objects from n, where order doesn't matter at all. The formulas are these: P of nr equals n factorial divided by the quantity n minus r factorial, and C of nr equals n factorial divided by the quantity r factorial times the quantity n minus r factorial. There's a symmetry worth remembering. C of nr equals C of n, n minus r. Choosing which R objects to include is exactly the same count as choosing which n minus R objects to leave out. Pascal's rule connects combinations recursively. C of nr equals C of n minus 1 R minus 1 plus C of n minus 1 R. The pigeonhole principle is deceptively simple but powerful. If you place n items into m boxes and n is greater than m, then at least one box must contain at least the ceiling of n divided by m items. You genuinely cannot spread them out evenly enough to avoid it. And the binomial theorem gives the full expansion of any power of a sum. The quantity x plus y to the n equals the sum from k equals 0 to n of c of nk times x to the power n minus k times y to the power k. Let's prove Pascal's rule properly, using a combinatorial argument rather than algebra. Fix one particular element, call it S, sitting inside a set of n elements. Now think about any R element subset you could choose. Every single one falls into exactly one of two categories. Either it contains S or it doesn't. There is no third option. Count each category separately. If the subset contains S, you've already used one of your R slots on S, so you just need to choose the remaining R minus 1 elements from the other n minus 1 elements, giving C of n minus 1 R minus 1 ways. If the subset doesn't contain S, you need to choose all R elements from the remaining n minus 1 elements, giving C of n minus 1 R ways. Since these two categories are disjoint, no subset can be in both and exhaustive. Every subset falls into one or the other. The total count is simply the sum of the two. C of nr equals C of n minus 1 R minus 1 plus C of n minus 1 R. Proof complete. Here's why the division by R factorial in the combination formula makes sense. C of nr equals P of nr divided by R factorial because every unordered group of R objects corresponds to exactly R factorial different ordered arrangements of that same group. Dividing by R factorial simply removes those extra orderings you don't care about. Here's the trick. Run through 3 questions in order every time you face a counting problem. Question 1. Does order matter? If yes, it's a permutation. If no, a combination. Question 2. Are repeats allowed? This changes the formula entirely. Arrangements with repetition allowed come out into the power R, a completely different formula from P of nr. Question 3. Are there restrictions? Must certain items be included or excluded? Handle those first, then count the remaining freely chosen items separately and multiply the two counts together. Worked example A. A straightforward permutation. How many ways can you arrange 5 different books on a shelf? Order clearly matters here, and all 5 books get used, so this is P of 5 equals 5 factorial equals 120. Worked example B, a straightforward combination. How many ways can you form a committee of 4 people chosen from a pool of 10? Order doesn't matter for a committee, so this is C of 10, 4 equals 10 factorial, divided by the quantity 4 factorial times 6 factorial equals 210. Worked example C, a restricted counting problem. From a pool of 6 men and 4 women, choose a committee of 5 people, with the restriction that exactly 2 must be women. First, handle the restriction. Choose exactly 2 women from the 4 available. C of 4, 2 equals 6 ways. Next, count the remaining freely chosen part. The other 3 committee spots must come from the 6 men. C of 6, 3 equals 20 ways. Since these 2 choices are completely independent, multiply the 2 counts together. 6 times 20 equals 120 total committees. Worked example D, the pigeonhole principle in action. Prove that among any 367 people, at least 2 must share the same birthday. First, there are 366 possible birthdays in total, our boxes, including February 29th for leap years. Next, we have 367 people, but only 366 possible birthday boxes to place them into, and 367 is strictly greater than 366. By the pigeonhole principle, since we have more people than available birthday slots, at least one box must contain at least 2 people, meaning at least 2 people are guaranteed to share a birthday. Proof complete. Notice this is a pure existence proof. It doesn't tell you which 2 people share a birthday, only that some pair definitely must. Finally, common mistakes to watch for. First, using the permutation formula P of nr when the objects involved are actually repeated or indistinguishable. That situation needs a different formula. In factorial, divided by the product of the factorials of each repeated group's count. Second, forgetting to multiply independent counting stages together, like in worked example C, choosing the women and choosing the men are separate independent decisions, and independent choices always multiply. And third, applying the pigeonhole principle with the wrong count for the number of boxes, get that count wrong and the entire argument falls apart.